Hello and welcome to zwitterstat. In this video, we are going to learn about matrices from an introductory point of view. So let's get started. Let's say we have a simultaneous equations in two variables. Our first equation is 2x plus 3y equals to 6, and our second equation is x plus 2y equals to 4. Now we are asked to solve this system of equations and to check whether a common solution exists or not. So the most common approach that we have learned in our earlier maths classes is the elimination method. And how we are going to do it? We will multiply the second equation, that is x plus 2y equals to 4, by 2. So we will get 2x plus 4y equals to 8, right? 2x plus 4y equals to 8, that we got after multiplying equation 2 by a fact by 2. And we are going to subtract the first equation, that is 2x plus 3y equals to 6, from 2x plus 4y equals to 8. So 2x cancels with 2x, 4y minus 3y, that is we are left with y, and 8 minus 6 is 2. So we get y equals to 2. And when we substitute this y equals to 2 in our first equation, that is 2x plus 3y equals to 6, we get x equals to 0, right? So this is the most basic method that we have learned for solving a pair of simultaneous equations, right? We have simultaneous equations 2x plus 3y equals to 6 and x plus 2y equals to 4. So any such simultaneous equations can be solved by elimination method, right? So now let's look at it from a geometrical point of view. Here is our x-axis and y-axis, and we have uh, divided our x-axis into we have marked the various numbers on x-axis 1, 2, 3, 4. Each unit is of size 1 on both y and x-axis, right? So we plot the lines, both plot both the equation, that is 2x plus 3y equals to 6 and x plus 2y equals to 4, on our graph, and we will see where these two lines meet. So from a geometrical point of view, we try to look at how these two lines meet. If they meet at a common point, they have a common solution. If they don't meet, there it means there's no solution exists. There's no common solution. And if these two lines completely superimpose each other, then we have infinitely many solutions for the simultaneous equations. Right. So from the geometrical point of view, the simultaneous equation in two variables are nothing but a pair of lines, right? We need two variables x and y to define a line. So simultaneous equation in two variables are nothing but two equations of a line, and we have to check whether they meet at a common point, whether they superimpose each other, or whether they are parallel to each other, that is they do not meet at all. Here it is. If they are parallel to each other, there is no solution, no common solution. If they completely superimpose each other, there are infinitely many solutions. And if they meet only at a single point, then one solution exists. Right? Now, now, as I said in the start of the video, we are going to learn about matrices. So you might be wondering what matrices are and what it has to do with these equations, these simultaneous equations, right? So the idea of matrices is to neatly collect the idea, or I can say neatly present the idea of solving simultaneous equations, right? Matrix is nothing but an array of numbers, right? Now the idea of simultaneous equations, we need to solve the simultaneous equation in order to get a solution, because a bunch of simultaneous equations may represent a system, right? different system, thermodynamic systems. We may talk about the just like the a quantum mechanical system. The various properties of the atom, electron are represented by a bunch of equations, and we need to solve these equations to get a solution, right? So how we are going to do it? When the variable increases and the number of equations increases, a manual elimination method is a very tedious one. And here, to rescue from this tedious process, matrices do help in a great way. So look at here. Here, I'm taking the same example that we have solved from elimination method to give you the idea what a matrix is, and then we will create a general representation of a matrix. So I have created a matrix of two rows and two columns. This is the first, sorry, this is the first row, this is the second row, and this is the first column, this is the second column, right? So a matrix is nothing but an array of numbers. So here I'm having my array of numbers consisting the coefficients of my equations. 2 and 3 are the coefficients of x and y respectively in the first equation, and 1 and 2 are the coefficients of x and y respectively in the second equation. And I call such a collection of numbers a matrix. So I gave name to the matrix A, capital letters A, B, C, D, and other letters I use generally A, B, C, D are used to represent a matrix. And small letters such as X and B are used to represent a vector. A vector is nothing but we can say a special name for a column matrix or a row matrix. But why we name it as vectors, what it has to do with the geometrical vectors that we have studied in physics to understand motion in one and two dimensions, right? So it is closely related to that idea, and in later videos we will surely see how how it is related to the geometrical idea of vectors and what it is, right? So in the later videos we will discuss it. Let's stick to the idea of what a matrix is, right? So I've named my the matrix that is consisting the coefficients of the two equations, that is 2x plus 3y equals to 6 and x plus 2y equals to 4. So I've named this matrix A, and I've named this vector as x small x, and this second the second vector that is on the second collection of numbers that is consisting 6 and 4, we can say the constants, uh, as vector B, right? So we represent vectors by small numbers and matrices by capital small numbers, sorry, not small numbers but small letters, and matrices by capital letters, right? And we often call it, and I like calling this equation as ax equals to b. So matrix multiplied by a vector consisting of the variables x and y equals to a vector b, which is having two elements, element 6 in its first row and element 4 in its second row, right? So ax equals to b is the matrix equation. Now you might be wondering how the elimination method is tedious compared to this matrix, the new and weird looking representation of these equations. Now, for two variable, two equations, two these simultaneous equations, the elimination process may not be tedious. But as the number of equations increases and the number of variables increases, the process eventually becomes so tedious that it becomes nearly impossible for a person to solve all these equations manually. So, in the study of matrices, we have developed there were various mathematicians like Gauss and other mathematicians as well. They have Jordan. They have developed a bunch of algorithms that we apply and can easily solve the system of equations. And sometimes without even solving the system of equations, we can study the properties of matrices and tell whether the system of equations will have a common solution, or whether they have infinitely many solutions, whether they have a no solution, right? So it saves a lot of time. So, as I've said, in general, a matrix is an array of elements. Now, these elements can be functions. It may be cos of x, sine of x, natural log of x, log to the base 10 of x, any transcendental functions or any other function which you can imagine, polynomial functions, some or the other thing, right? And it may be numbers, not only real, but it can also be complex numbers. We have complex matrices as well, and complex matrices is useful in the study of complex analysis, as well as in the field of physics. It is important from the point of view of quantum mechanics and other various areas of physics acquire the idea and the principle of complex matrices, right? So now there's something associated with the matrix. We have seen that matrix has a row and has a column. So we associate or tell how we tell how many rows and columns are, or how one matrix is different from the other. And that is we we do with the idea of dimension. A dimension of a matrix is nothing but it tells how many rows and how many columns a given matrix has, right? So when I say I am having a matrix of 2 cross 2, just like the matrix that we have previously seen, uh, 2 3 1 2, the first row having elements 2 3 and the second row having 1 2. So there are 2 rows and 2 columns. So it is a 2 cross 2 matrix. The number of rows are 2 and the number of columns are 2, right? Number of rows are 2 and number of columns are also 2, right? So in general, we represent the dimension of a matrix by m cross n, where m represents the number of rows and n represents the number of columns. So a general matrix representation can be written like this, where there are m rows and n columns. And here in the subscript we have written 1 1 1 2. So it tells about the position of that element in the matrix. An element marked with A11 tells that in the first row and in the first column, we'll search for the first row. Yeah, this is the first row. And then we say there's an element in the first column and the first row. First column, this is the first column, this is the first row, and the element common to both the first column and the first row is A11. Similarly, element common to first row and second column. First row, second column A12. Right. So these notations A11, A12, and these numbers in the subscript 11, 12, 1n tells us about the position of the element or the different numbers in the matrix. Right. So in general, we write a matrix A is equals to Aij, and inside the square bracket and outside the square bracket in the subscript we write m cross m, where m cross m represent the dimension of the matrix, number of rows and number of columns. Now I and j are the general representation for the element aij in the ith row and the jth column, where I ranges from 1 to m and j ranges from 1 to n. The number of columns are n and the number of rows are n, right? So this was all about matrices and why do we need matrices. And in our later videos, we will learn about the properties of matrices, about vectors, about the different algorithms that are involved in matrices, right? And the types of matrices. So stay tuned. Thank you.